Hello, I'm Sangrok Lee, a cybersecurity researcher. So today I'd like to introduce our approach to cross-architectural dynamic analysis of Linux malware. First, the distinctive feature of Linux and Linux malware are explained, and why they cause problems in malware analysis. Next, I will outline our dynamic analysis approach for Linux binaries, focusing on the interpretation and recompilation of LLVM IR. Lastly, I will demonstrate the effectiveness of our method with the evaluation result from the Linux core utils test suite. Linux has a broad application spectrum being utilized in web servers, supercomputers, PC, Android, and IoT devices. The most distinguishing feature of Linux is its diversity. It can operate on a vast array of CPUs, from Intel to ARM, BIPs, PPC, and beyond. This diversity is amplified by the range of C libraries. C libraries we use for functions such as printf or thread. Instead of relying solely on the GNU C library, we often utilize lighter alternatives like Muscle or UClibc. Moreover, when we consider IoT devices, the situation becomes even more complex. Unlike PC, these devices lack a standardized hardware design, which adds another layer of variability. Like Linux operating system, Linux malware has also been observed to target a wide array of CPUs. The research paper titled Understanding Linux Malware sheds light on this aspect. It illustrates that Linux malware isn't confined to attacking Intel CPUs alone. Its targets cover a vast spectrum, even extending to PowerPC. This underscores the wide range of CPUs that Linux malware can target and run. The diversity of Linux and Linux malware poses significant challenges in dynamic malware analysis. Runtime environments for dynamic analysis encompass a wide range of factors, including CPUs, C libraries, and hardware architectures. This results in an extensive variety of execution environments. Creating virtual images to cover all possible combinations is nearly impractical. Using real devices comes with its own limitations. Commercial devices normally restrict shell access, making tool installation difficult. Additionally, the limited computing power of IoT devices may hinder the execution of analysis tools. And the number of analysis tools also very large if we consider the CPU and libraries. The diversity of Linux presents challenges not only in dynamic analysis, but also in static analysis. Analysts must know in-depth knowledge of machine language for every CPU type, but this is nearly impossible. Furthermore, existing decompilers have limited support for different CPUs. So our goals for the dynamic analysis of Linux malware are as follows. Firstly, we aim to develop a dynamic analysis tool that supports a wide range of CPUs and includes key analysis features like debugging, dynamic instrumentation, and micro-execution. Secondly, we want to facilitate dynamic analysis within a single host runtime environment, removing the requirements for separate emulators or physical devices. To achieve this, we are using LLVM IR, interpreting, and recompiling. Third, we plan to boost dynamic analysis by integrating static analysis technique. This diagram illustrates an overview of our system. First, we convert the binary into LLVM IR. Once in IR, we restore symbols, such as functions and variables. With this IR as an input, we perform dynamic analysis through interpretation, which include debugging and instrumentation. And the other side, we use binary rewriting, so we can conduct behavior monitoring through static instrumentation. Our first stage is disassembly. In converting a binary to LLVM IR, the foremost critical task is extracting code from the binary. To achieve this, we employ linear sweep disassembly. Recursive traversal disassembly can cause code coverage issues when we encounter indirect branches. For the stability of the generated IR, it is vital to eliminate such problems. While linear disassembly solves these issues, it can misidentify data as code, leading to inaccuracies. To address this, we've developed the superposition method, permitting the coexistence of correctly and incorrectly identified code blocks within the IR code, even though they overlap in address space. And the other is we use error propagation algorithm that is developed in previous papers. After extracting codes, once the code blocks are recognized, we convert them into tiny codes. The tiny code is IR used by QEMU. And then we transform this tiny code into LLVM IR. Using QEMU's tiny code is already suggested in the previous works, such as libqemu or Revenge paper. By adopting this approach, we can reduce potential bugs that may arise from handwriting the conversion of each CPU's machine code to IR. Moreover, it allows us significant savings in terms of effort and time. Ensuring our generated IR is executable requires careful CPU modeling. Each CPU has a unique set of registers which primarily store execution result. To run the IR on the host architecture, we must map the target CPU to host CPU. Two potential CPU modeling approaches are available. The first is one-to-one direct mapping, like Apple's Rosetta 2, allowing the x64 binaries to run on ARM silicon. However, this method is optimal for only one source CPU and one destination CPU. Our environment is many source CPUs and one destination CPU. So we use virtual CPU modeling. So in LLVM IR, virtual CPU is represented only as a structural variable. So it is flexible, but a little bit slow than compared with one-to-one direct mapping. For IR to run on the host, it needs to interact with the host environment. This means the IR has to align itself with the data types expected by the hosts, libraries, and kernel. Consider the system call like read function as an example. For 32-bit big endian MIPS CPU, the argument types for the functions such as long, integer, and character pointer are all 4-byte lengths. But in 64-bit Linux host, all types except for integer have a length of 8 bytes. And furthermore, due to the difference between little and big endian, that data values need to be swapped when being sent to and received from the host. To empower dynamic analysis further, we have incorporated a symbol recovery. In the compilation process, functions and variables information are removed. Restoring these from the binary allows us to extract more accurate and human-readable information during dynamic analysis. Symbol recovery algorithms have been outlined in the compilation-related papers, and we mainly utilize these approaches. In this presentation, we aim to briefly showcase what we have added to these existing methods. Scripted binaries often lack function information. In such cases, the most accurately restorable symbol is the system call function. Modern CPUs have explicit system call instructions, and there is an explicit register to store system call numbers. So we can restore system call function when we can calculate system call number, but the system call number is easily calculated using IR constant calculation. For identifying function types, use before I define and define before return strategies are used normally, and we follow these also as a starting point. In estimating the number of function input arguments, we take a conservative approach. Essentially, it is safer to have an excess of arguments than a shortage in aspect of execution stability. So we initially find types of leaf functions. In here, leaf function means function which do not call other function. Starting from these leaf functions and system call functions, we progressively identify the types of other functions, searching backward in call graph. Whenever there are load and store commands involving the step pointer register, it is highly likely that stack variables exist based on the value of stack pointer register. So finding stack variable can be challenging when a function has indirect branches whose target addresses remain unreserved. However, if there is complete path from the function entry to return point, we can identify these stack variables by moving backward from the return point. And this is addressing symbolization error is crucial for us as we aim to generate executable IR. For unreserved indirect branches, we utilize a runtime lookup table. This table inserted into each function help to identify target basic block for each indirect branch target at runtime. A second issue arises with incomplete function boundary recognition. In the presence of unidentified functions that might be called at runtime by indirect call instructions, we've created an umbrella function. This function encapsulating all the binary file code inside it. Third, we encounter incomplete data symbol recovery situation. Here we load the original binaries data at its original address, allowing this data to be accessed even when data symbol wasn't restored. Lastly, linear sweep disassembly can sometimes inaccurately recognize data as code. This is especially prevalent with variable length instructions like Intel, resulting in accurate and inaccurate code overlap in the address space. So we solve this problem by superpositioning IR. So previously developed factors, we devised 3 dynamic analysis methods. First, we adopted dynamic analysis via IR interpretation. We've implemented features such as debugger, dynamic instrumentation, and microcode execution, and forced execution into the LLVM interpreter presented in LLVM project. Though this interpretation approach is most conducive to analysis feature implementation, it does suffer from slower execution speed. So second dynamic analysis is using binary rewriting. We've constructed an approach that involves appending behavior analysis IR to the IR converted from the binary, generating a host binary, and running it on the host. This binary rewriting approach enables swift execution and allows instrumentation at the function, block, and instruction level. Our third approach involves a hybrid analysis, which blends both interpreting and binary rewriting techniques. With this method, areas of code that require detailed analysis undergo interpreting-based analysis, while library functions and already analyzed code can be executed by switching to the rewritten binary. The feasibility of execution switching between rewritten binary and the IR interpreter owes to 2 key factors. Firstly, as both utilize the same LLVM IR, the code and data remain consistent in the execution address space. Secondly, the use of the virtual CPU model made it possible to pass execution result from one execution domain to the next domain. In other words, the preservation of execution context was made possible through the virtual CPU. In the memory space, there is a single virtual CPU variable that is visible to both the interpreter and binary. Originally, interpreting and binary execution were considered separate programs. Through engineering effort, we set up trampoline points in the interpreter and binary. This trampoline allowed for jump to another execution domain. As a result, we made hybrid analysis possible. We evaluated the accuracy of our binary writing implementation, as well as the stability and speed enhancement of our hybrid execution method. First, to measure the accuracy of binary writing, we used the test suite provided by Linux core utils. We created the sample binaries using different libraries. For 64 Intel binary, we used glibc. For ARM, we utilized uclibc. And for MIPS, we employed muscle library. The results showed success rate of 93% for MIPS, 91% for 64-bit Intel, and 83% for ARM. Our work is in progress. Currently, we are in process of implementing system calls related to multi-thread and signal handling. So, because of these factors are contributing to the execution errors. Using core utility samples, we measured the speed up achieved by switching execution between interpreter and binary. So the table only showcases a portion of the whole result, but we saw a speed up range from 5 to 99%. We found that binaries with a heavy disk I/O, like LS or DF, showed higher speed up result. This is graphical view of speed up. So this is conclusion. So we showed that our strategies for building cross-architectural dynamic analysis and implemented based on those. And the evaluation results showed correctness and stability of our dynamic analysis method. There is some future work. The big one is related to dynamic link library. So, and second one is peripheral emulation or simulation. And this finally, last one is a fine-grained execution transition. In instruction level transition, we plan to research. Thank you.
Questions, perfect.
Yeah. So thank you for your talk. I have a small question about your experiment 1. So you measured the success rate for the correctness, right? Could you comment on how exactly you measured this?
Pardon?
So here in this experiment, you were providing the success rate. How exactly did you measure the success rate?
This is skip is we do not consider skip. Only if pass and fail is considered in here.
So it's the regression tests or it's some sort of tests that were already there for these core utils.
Sorry for my poor English.
No, not a problem. So it's the make check. I read it on the slide. Thank you.
One more question.
What compiler flags did you use for these tests? Did you compile with optimizations or debug info?
The 64 Intel CPU, we use GCC.
Mm-hmm.
And for ARM, we build root the building system. So maybe there is also GCC, but UCLibc we use for library.
And did you use debug messages or stripped binaries?
We did not use debug information, but library symbol does not stripped out in this case.
Mm-hmm.
Yeah.
Yeah, I think that's already really good because binary rewriting is very difficult to get the program running. So achieving a high success rate is very hard, I guess.
But some people in our company debate and not good for me. They said bad result.
Oh, really?
Yeah.
Yeah, but they don't do the research. Maybe they should try it, and then they can.
Yes, they
say.
are other parts.
Yeah.
They are not our team.
Okay, there are no other questions. Guess we can thank the speaker again. And